Welcome back everyone, my name is Pedram and this is where we do advanced time series analysis, deep forecasting. Alright, let's begin our deep forecasting journey. Module 1, Demystifying time series data and modeling. In this module, we will go over some time series basics, we will define some terminology when it comes to forecasting, and we will cover different aspects of time series modeling at a very high level. And by the way, this photo was created with DALL-E, which is OpenAI's image generator. And hopefully this is you when you graduate from this course. You will get your very own shiny crystal ball here, right? And what you want to forecast with this shiny crystal ball is really up to you. But typically, the first thing that comes to mind is that, can I forecast stock prices with it, right? This is a big question. Well, let's see, after all, I'm here to make sure that you're not using this crystal ball incorrectly. This is a super powerful tool. You can absolutely use it for any kind of time series forecasting, from demand forecasting to sales, weather, economic data, marketing, healthcare, you name it. But when it comes to stock price, you want to be extra careful because this crystal ball can become overpromising and misleading, of course. So the good news is that I will talk about all the details of stock price prediction in this course, as well as any kind of time series prediction. Here are the key topics. We're going to do it in 4 parts: time series basics, modeling, forecasting, and then finally, can we beat Wall Street, right? Starting with time series basics, we will answer questions like this. What is a sequence data? What do we mean by that? What are different time series tasks? What are different time series components? We will cover some concepts like trend, seasonality, stationarity, and things like this, because we need them when you're building the models. But before jumping into the model building, we need to talk about forecasting strategies and clear some terminologies there, right? So this is the part that is typically overlooked by many practitioners out there. So I want you to pay very good attention. So for example, when you're forecasting, are you talking about one step ahead forecast or multi-horizon forecast? If it is multi-horizon, are you making those forecasts at the same time? We call it multiple output. Or you're doing it iteratively. We call it multi-step, right? So we're going to cover all these things. And then, are you doing univariate time series forecasting or multivariate time series forecasting? And you will see that in this course, we will mainly focus on univariate. We're going to talk about the models that can handle multivariate, but we're going to talk about the challenges as well. And then most importantly, we will cover some benchmarks, right? Because in time series forecasting, we will see later on that sometimes it's simply very hard to outbid a very simple benchmark. For example, if your data set is stationary, a good benchmark is just simple average. Can your model outbid the simple average model, right? So things like that. Then in the modeling section, in this video, we're going to talk about, at a very high level, what is the difference between econometric approach, machine learning approach, and deep learning approach? Why we need to go beyond our classical models. And finally, we're going to answer this question that, can we beat Wall Street, right? But in order to do that, so we have to talk about efficient market hypothesis and see if the stock price market is random walk or not, right? Regardless to your answer to that question, that if the prices are random walk or not, we want to see if univariate models literally work for stock price, and then if not, can we make them better, right? And then finally, we're going to answer this kind of philosophical question about, okay, so what? So we're going over a deep forecasting course, and at the end of the day, can I literally use it for stock price predictions? What are the challenges or not, right? So we're going to focus on these things at the end of today as well. So hopefully by the end of today's lecture, you have a clear idea that what this course is about, and more importantly, what it is not about. All right, Module 1, Part 1, Time Series Basics. All right, so starting with the definition of sequence data. What is a sequence data? Sequence data refers to any data that has a specific order or sequence to it, right? And so these are different types of sequence data. We can have time series data, we can have text data, because the character of a text come in a sequence, right? And we can have audio or video, right? What we're focusing in this course is basically time series data. Within time series data, we can have regular time series or irregular time series. So the regular time series, as the name suggests, data is recorded at regular time intervals, which are equally spaced data, right? It can be seconds, minutes, hours, days, month, and you name it. Examples are, for example, daily stock price, monthly airline passengers, hourly temperature, quarterly sales, and things like that, right? And irregular data is the data which is recorded at irregular, uneven intervals, right? So the examples are, for example, ATM transactions, emergency room admissions, website visits, so things like that. In this course, we'll be focusing on regular time series, right? And the reason is that the modeling approach for each of these types of data might be different. Not all the models, especially the classical models, for example, ARIMA or the econometric models, cannot handle irregular time series. So if you have irregular time series, you need to do some pre-processing and make it ready to pass it to those classical models. Or you can go ahead and use some other models that can handle irregular time series. Later on, we're going to discuss which models can handle them, which models cannot. For example, just a simple example, a simple LSTM, as a deep learning model, can handle irregular time series. But when the time comes, we're going to talk about all those details. Now, what are time series tasks? We can have time series forecasting, time series classification, time series clustering, and anomaly detection or event detection. So starting from time series forecasting, what is it? Forecasting is predicting future values of a time series based on its historical data. It can be either qualitative or quantitative, right? So what is qualitative time series forecasting? Qualitative forecasting is going to leverage expert opinion, judgments, gut feeling, or you can think of it as subjective insights to make forecasts. So we use it when there is new situations or when we have data scarcity, basically when there is no historical data in some cases. So what are some examples? Examples include, for example, you're launching a new product when there's no historical data for that, or you are incorporating economic disruptions in stock price predictions. For example, who knows when is the next pandemic, right? When is the next war? This kind of forecasting can involve you can think of it as gut feeling as well, or subjective opinion. Then another type of time series forecasting is quantitative. So this is, let me actually highlight it. So this is our quantitative time series forecasting. And as the name suggests, it relies on numerical data and statistical models to predict future outcomes. So the examples are, sales forecasting, stock price prediction, utility consumption, weather forecast, and you name it. In this course, we're going to focus on this kind of forecasting, quantitative time series forecasting. And it also depends on a big assumption. And the assumption is that past pattern will continue. So obviously, the stronger this assumption, the better forecast we have. And if you're dealing with time series that this assumption does not hold, like stock price prediction, then you kind of get a sense that your forecasts are going to be less accurate. Now, what are other types of time series tasks? The next one is classification. So this is the next one. So classification simply means assigning labels to time series data. For example, you want to identify ECG patterns for heart condition. Is it normal? Is it arrhythmia? Or is it something else, right? Or for example, you are wearing this wearable device, you're having your watch, and then you want to classify your movement patterns. So basically, your watch is collecting information over time, and it's going to classify if you are walking, running, sleeping, or what, right? So this is time series classification. Another task is time series clustering. So clustering simply means grouping similar time series together without predefined labels. So there's no label here. This is kind of if you're familiar with the term unsupervised, this is kind of unsupervised, right? The goal is to put some time series together that they behave similarly, right? So for example, we can use it for customer segmentation for marketing campaigns. You can keep track of your clients' purchases, the dollar amounts, the dates, and etc., and identify their spending trends. Then later on, you can, based on those trends, you want to send them, for example, some coupons or give them some club memberships or some marketing announcements, things like that. The next one is anomaly or the event detection. So the idea is that, so imagine you have a time series that's showing migration pattern between two different countries. So for example, this is what we have. This is migration from country A to country B over time, right? And as you can see, at some point in time, there is this strange behavior. If this behavior is not expected, we call it outlier, anomaly, and we're trying to detect that anomaly. And if that strange behavior is kind of expected, we call it event detection. Example is like hot word detection. So when you say, for example, your phone is constantly listening to you, and then when you say, hey Siri, something is triggered, and basically that event is detected. But that event is kind of expected. So these are different time series tasks, and as I said earlier, we are focusing on, let me use my highlighter here. We are focusing on quantitative time series forecasting. Okay, let's look into more forecasting examples. I want you to think about which of the following examples are easier to forecast, right? I'm going to give you 5 options, and then you go ahead and pause the video and try to rank them and think about which one is easier or harder compared to the other one in order to forecast into the future, right? So the first one is, time of a sunset this day next month. The next one, Apple stock price tomorrow. The next one, airline ticket demand or price next year. Number 4, new car model sales in the first quarter. And number 5, monthly rainfalls in Utah or any other states next winter, right? So I want you to pause the video and think about it. Which one is easier, which one is harder to forecast into the future? All right, so here's how I rank them. I would say number 1 and 5 are the easiest ones. We show them with green. Then number 3 and 4, we show them with blue. And then final number 2 is going to be the hardest one. But why? What makes it easier or harder to forecast one time series versus another one? In other words, what impacts forecastability, right? So here are some of the factors. The first one is data availability, right? How much historical information we have, right? Basically, if the more information we have, the better models we can construct, and then the more powerful forecasting engines we're gonna have, right? The next one is how similar the future is to the past. I.e. if the past patterns will continue or not, right? And then finally, either we have a good understanding of the underlying factors or not, right? So let's go back to the examples. So we know that for number 1 and 5, in general, basically the astronomical and climate events like sunset or rainfalls follow precise and predictable patterns because we have extensive record of data and good understanding of the underlying factors. Yes, you might say that for rainfall, maybe we're not good at making daily or hourly predictions, but when it comes on a monthly basis, we can get pretty accurate forecasts. However, for number 2, for example, number 2, Apple stock price tomorrow, even though we might have access to large amount of historical data, but the thing is that how similar is the future to the past? If anything, you probably have heard it, this disclaimer a million times when it comes to stock price. Past performance does not guarantee future results, right? Besides, what are the underlying factors for a stock price? There's a zoo of factors out there, from technical to fundamental indicators, or macro factors, company-specific factors, and et cetera, right? This is what makes it extremely difficult to forecast, for example, Apple stock price tomorrow, right? So what I'm trying to say is that, what you should take away is, depending on the nature of your time series, the forecasting models that you're going to learn in this course might be either promising or disappointing. So that's the nature of time series forecasting. And for that reason, throughout this entire course, we will stick to 2 extreme examples of time series data. One, which is very well behaved, the one on the left-hand side, airline passenger monthly data. This is a very classical time series, monthly time series data from 1949 to 1960. And on the right, this is Apple stock price using daily data. And the idea is that we're gonna, throughout the course, we're gonna construct time series models using econometrics, machine learning, and deep learning, and apply those models to these 2 extreme time series and see how they perform in terms of making forecasts into the future. And obviously, if you can handle these 2 extremes, you can take care of anything in between, right? So this is basically what we're gonna use as a data set for the entire course down the road. All right, now let's talk about time series decomposition. Basically, the idea is that Let's break down a time series into its components, namely trend, seasonality, and whatever is left over, we can call it remainder or residual. Don't worry about the details. Later on in the course, we're going to talk about how we can drive these things. But at a high level, let's understand what are these, basically the ingredients and why do we need them? Because as I said earlier, later in the course, when we're creating models, imagine you're putting together some classical models. You have to know what are the ingredients, right? So, and then you can add them in a linear fashion or nonlinear fashion, right? For more complex models like more non-parametric machine learning models or more advanced deep neural network models, we may not need to specifically engineer these basically components, but it is regardless it's beneficial to break down a time series into its components and at least visually see if there's something there or not, right? So let's look at start with our very well-behaved data set, right, which is airline passengers. So this is what we have. And as you can see, if you just pay attention to this chart, you see there's a clear upward trend here, and it seems that there is some clear seasonality. And it seems that we can break down this, basically time series into its components, and this is exactly what we're doing. At the top panel, we have the original data set. Pay attention to the scale, which is between 200 and 600, right? So this is number of passengers per month, right? And this is old data. And then this is a trend component. The trend component basically shows the overall direction the data is moving over a long period, right? It can be upward, it can be downward, it can be stable, and it can both go up and down, right? So we can, it can go up first and then come down. Then the next component is just seasonality, right? Seasonality is showing the regular patterns that are repeated over a known fixed period, like day, week, month, or quarterly, right? So this is very typical in retail sales and energy consumptions, or in this example, airline passenger data, where there is a seasonal influence. And I want you to pay very good attention to the units, right? So the magnitude, it's between -50 and 50. So this is relatively large compared to the original scale of the data. So it means that the seasonal component is strong and the magnitude is large, right? So this is airline passengers. So for example, summer, obviously we have more passengers compared to other seasons, right? And then finally, if we take out the trend and seasonality from this data set, we're going to end up with something called residual. We call it remainder as well. So the remainder or residual represent the noise or randomness once trend and seasonality have been accounted for. So if you still see a pattern in the remainder or residual, it means that your decomposition was not enough to capture all the nuances in the data, right? So obviously, when you're creating a model, you have to say, okay, I cannot simply break it down into trend and seasonality and then put it together. So maybe there's something more to that. But in this case, I don't know. This is not necessarily bad, but the problem with this, look at that. Here we have more magnitudes in terms of residuals compared to here. So there are ways to fix that, and we're going to look into all those details later in the course. So this was the time series decomposition for our well-behaved data set. Now let's look at the same decomposition for our not well-behaved data set, which is the stock price. Okay, so here let's use the same decomposition for Apple stock price in the past 600 business days from 2022 and until 2024. And then let's see what do we get if you just want to simply break it down into its components, right? So here's the original data set, right? So this is original adjusted close for Apple stock price. Look at the scale, 200, 150-ish. This is just simply the price. And then if I want to take the trend out of it, it's everything is basically the trend, right? And by the way, we can, if there's upward and downward trend, or if there's any cyclicality, it's going to show up here as well, right? And then look at seasonality, right? So seasonality, as you can see, you might think that, okay, maybe there's this seasonality going on, but pay attention to the scale. It's nothing. It's compared to the average price of Apple's stock price, I don't know, in the past 600 days, which is 160-ish. Then this seasonality scale is 0.1. It's nothing. So this is telling me that, basically, if you want to make a forecast for Apple stock price, you have to basically predict the trend, and it's everything, right? So and is it an easy task is it upward sloping? Is it downward sloping? What is it? This is basically the entire thing that you're trying to forecast. And obviously, if you look at the residuals, this one is also all over the place. We're going to talk about all these things later down in the course. But the point is that, as you can see in the previous example, when the airline passenger was a well-behaved time series, when we break it down to its components, trend, seasonality, we can easily see that the magnitude is large. If you're building a model together, you can say, hey, this is trend, this is seasonality, let's add it up, let's come up with a model. This is our classical ETS model, by the way. We're going to look into that in the next module. But for stock price, it's complicated. It seems that everything is going to be in the trend, and this is not easy to forecast, right? All right, now that we know what are the time series components, let's look into some statistical tools that are going to help us model time series from scratch, right, later on, right? These are basically components of our time series. So the first one is ACF, which stands for autocorrelation function. So ACF is a statistical tool that can be used to measure the autocorrelation of a time series. I bet you already know what is a correlation between two random variables, right? Autocorrelation is simply a measure of correlation between a time series and its lagged version. So let's look at our airline passenger data, and just let me use my marker. So imagine we have YT, this is our random variable, which is airline passenger, right? And I'm just making up some numbers. So starting from day one, let's say day one is 100. So month one's right. Month 100, month 205, and etc. Right? 105, 110, and then 108, for example, and things like that. So imagine this is our data set, right? And now if I go ahead and create our lag variable, so YT minus 1. So obviously we don't have observation for day one, for month 1. Then we are going to have 100, 105, 110, etc. Right? So this is our two random, well, basically random variable with its lag value. If I calculate the correlation between the two, I can get a number. This is our autocorrelation function, right? So this is a number. Let's say that number is 0.95, right? So this is the correlation between YT and YT minus 1. So this is 0.95. So they're highly correlated. This means that YT and YT minus 1 are highly linearly correlated or linearly related. Pay attention. Correlation is showing you nothing but the linear relationship. If there's any nonlinear relationship in a random variable and its lag value, correlation does not capture that. So just be aware of it. We talk about these things in the machine learning course as well. And basically, and then for example, let me use another color. If I go ahead and create YT minus 2, the second lag, YT minus 2, obviously there's NA here, and then we have 100 and 105, etc. So if I go ahead and calculate the correlation between these two, and then this is going to be the number, right? So the correlation is going to be lower, so maybe, I don't know, maybe 0.9 here. Obviously, as we go further back, this correlation is going to become weaker and weaker, because the correlation between, I don't know, today and yesterday, of course, is going to be a lot higher compared to the correlation between today and 10 days ago or 20 days ago. In this case, it's month, 10 months ago or 20 months ago. But why do we care about ACF or later on PACF? Because the thing is that we can use them as a diagnostic tools in terms of how many lag variables should we include in our model, for example. For example, later on when we're talking about ARIMA models, we're going to use ACF and PACF to tell us what should be the order of the model in terms of how many lags to use and etc. Right? And in general, ACF shows the degree to which the past values are predictive of future values, at least linearly, right? So for example, and it tells us something about the trend and seasonality in the data as well. Again, we can use them as diagnostic tools. For example, let me use the color red. So for example, when I look at this ACF, as you can see, there is this downward sloping in terms of the magnitude of autocorrelation, right? So this is clearly telling me that there's a trend in the data, right? So that's a sign of trend. And then if you see this scallop thing, this is a sign that your data has a clear seasonality. Why do we see that? Because pay attention, what is this thing, for example? This thing. This is the correlation between, if you count them, you're going to see it's going to be a correlation between YT and YT minus 12. So basically it's telling me that if you look at If you compare the airline passenger data, for example, December to December, and then each 12 months, they are going to be highly correlated compared to each other, right? So this is a sign of monthly seasonality in this data set. So again, in general, when you see this scallop thing, this is a sign of seasonality in the data. Depending on the frequency of the data, we can say, is it weekly, daily, monthly, and etc., right? So again, we can use ACF and PACF as some diagnostic tools. Okay, now what is PACF, or partial autocorrelation function? PACF measures the direct, here's the key term, direct correlation between time series and its lags, controlling for all the intermediate lags. For example, if I want to see what is the PACF at lag 5, basically it measures the direct correlation between YT minus 5 and YT, controlling for all the intermediate lags, meaning YT minus 1, YT minus 2, minus 3, and minus 4, right? So another example is what is PACF at lag 2? It measures the direct correlation between YT minus 2 and YT minus 1. Essentially, it looks for any leftover effect of YT minus 2 on YT that is not explained by YT minus 1 alone, right? So this is represented in pure correlational manner. So in simple words, the idea is super simple. Maybe YT and YT minus 2 are correlated simply because they're both connected to YT minus 1. Now, if you control for YT minus 1, what is the net correlation between YT and YT minus 2? So this is what PACF is capturing, and this is what was missing when we look at the ACF function, right? So let's go back to our simple airline passenger using monthly data. On the left, this is a data set, and on the right, we're looking at the PACF plots, right? So starting from lag 1, so this is PACF at lag 1. This is simply the correlation between YT and YT minus 1, and the autocorrelation and partial autocorrelation are pretty much the same. So let's say a number is 0.95, okay? So 0.95. And actually, I show you the autocorrelation function as well to compare it, right? So this is autocorrelation at lag 1, 0.95, and this is partial autocorrelation at lag 1, which is 0.95, right? Then when we go to lag 2, let me use another color. So this is lag 2. Let's start with the, here we go, autocorrelation on the left. This is autocorrelation. So basically this number, maybe it's 0.9. And actually, as you can see, it's a large one. So this means that the correlation between YT and YT minus 2, not controlling for anything else, is large, is 90%, right? However, on the right-hand side, we're saying that if you control for lag 1, then the correlation, the direct correlation between YT minus 2 and YT is actually a negative number. Maybe it's minus 0.3, okay, something like that. Now, as the last example, let's go further into the lag. So for example, I don't know, 1, 2, 3, 4, 5, 6. Let's do lag 6, right? So here is, let me actually show you the lag 6 for autocorrelation. So let's say, again, this is a large number, maybe it's 0.7. So this is the correlation between YT minus 7 and YT, which is a positive large number. But here on the right-hand side, 1, 2, 3, 4, 5, 6, 7, here we are. And as you can see, if you control for lag 1 through lag 6, there's nothing much left in terms of correlation between YT minus 7 and YT. So this is what partial autocorrelation is capturing, and hopefully it makes sense. All right, so here is an exercise for you. I want you to think about how the PACF is going to look like for Apple stock price using daily data, right? So this is our adjusted close for Apple stock price using daily data. I want you to pause the video and think about how the partial autocorrelation function is going to look like. Intuitively, you want to see, for example, this is daily data, right? If you control for yesterday's price, is there anything left for price 2 days ago, 3 days ago, 4 days ago, right? And the answer is no, nothing. And this is very typical for stock price. Look at that. The partial autocorrelation in lag 1 is almost equal to 1, so maybe 99%. Basically, the autocorrelation between YT and YT minus 1, today's price and yesterday's price, is very, very, very highly correlated. No, 99%-ish. And if you control for that, there's nothing else left for the previous lags, right? So this idea is very simple. We're going to say, if you control for one lag, then you don't need to add any more lags to the model. At least this is capturing the linear relationship, right? So if you want to come up with a forecasting model, and if you want to forecast tomorrow's price, it seems that in a stock price, everything is reflected in today's price, right? And this is very, very common for all the stock price time series data set. So maybe if you want to come up with a simple benchmark model as a forecasting model, you can write something like this. We can write down something like this. So imagine this is your YT plus 1. Again, we're going to talk about the details of these models later on, but very simplistically, it seems that if you only include one lag, YT, and then some noise, that's it. This is epsilon t, right? This is going to capture, at least, based on this partial autocorrelation, this is going to be capture everything, right? So we're going to say tomorrow's price is nothing but today's price plus some noise. And later on, we're going to give it a name. This is our random walk model. And if you want to add this upward trend to that, you can go ahead and add a drift term to it. But the point is that we can use this as a benchmark to compare it with any other forecasting models, at least based on this partial autocorrelation, right? But just be aware, the partial autocorrelation is capturing the linear relationship between your random variables, right? So in this case, YT and YT minus 1, or YT plus 1 and YT. All right, before we wrap up part 1 of module 1, which was time series basics, I want to cover the concept of stationarity and what do we mean by that. So what is stationary versus non-stationary data, right? What makes a data set stationary? So I want you to look at these two time series on the right-hand side, and then let's label them A and B. And think about it. Imagine you know nothing about the formal definition of a stationarity. And which one do you think is stationary, which one is non-stationary? Yes, right? So A is going to be your stationary time series, and B is going to be your non-stationary time series. So what's going on? Why do you think basically what we were thinking, right? So the idea of a stationarity is very simple. It says that if the statistical properties of the time series does not depend on the time, then we say that that time series is stationary. So in this case, for example, we can what are the statistical properties? So for example, what is the mean? What is the variance? What is autocorrelation? What are the higher moments, right? So if the mean and variance and autocorrelation is constant through time, we call it weak stationary. If the higher moments are also constant, like kurtosis and things like that, we call it strong stationarity. So again, don't worry about these technical definitions. At least learn these things at a high level. When the right time comes, I will cover them in details. But we just figured out, okay, A is a stationary because it seems that it's more stable over time, and B is not a stationary. It's going up and down, and we don't know, if you want to go further into the future, we don't know what's the direction, right? So now I want you to think about the second question. So imagine here we have 1,000 time steps, and I want you to think about what does this time series look like for the next 100 time steps, right? So let me use another color, red. So for example, this is where we are, 1100, and you want to see where the time series is, right? So which one is easier to make a forecast for the long term into the future, A or B? Probably again A, right? Because you're going to say that, you know what, it seems that historical average for the first 1,000 time step is this. Now, if I want to forecast into the future for more 100 steps, maybe this is something like this. This is where the time series is going to, I don't know if it's going to lie, right? And it's a pretty stable forecast, I guess. But what about this one? What about, time series B? And if you want to forecast 100 time steps into the future, is it this one, or this one, or this one? Which one is it, right? So as you can see, for long term, the predictability of the time series in the long run, stationarity matters, right? So this is where we are. We say that stationary time series are easier to forecast because you can assume that future statistical properties will not change, right? So again, the idea is that if you are dealing with a stationary time series, your forecast into the future for multiple horizon long-term decision is going to be more stable. This does not mean that we cannot forecast non-stationary data set, right? This is simply another tool that we can think of. For example, in terms of pre-processing the data, if you have a non-stationary data set, you can do some magic. We're going to talk about that. You can use some tricks and make it stationary. And why do we care about it? Because if you're making a long-term, multi-horizon forecast into the future, we know that the stationary forecast, the forecast for stationary time series are more stable compared to non-stationary time series. All right, now that we know why we care about stationarity, let's talk about how we can transform a non-stationary data into stationary, right? So for example, in this plot, we are looking at Google closing price, which is obviously a non-stationary time series, and we need to see how can we turn it into a stationary time series like this. Again, why do we care? Because we know if the time series is stationary, with our long horizon forecasts are going to be more stable compared to non-stationary data set, right? So there are different ways for this transformation. The easiest one is what we call differencing. Differencing is very simple. It's computing the difference between consecutive observations, right? So for example, this is your original data on the left. So imagine this is your original data. And in time step 1, we have 10, we have then 12, and etc., right? 8, 14, and 7, right? So the idea of differencing is that simply we can do difference it once, right? Simply, what is the difference between yt and yt minus 1, right? So 12 minus 10, 2. 8 minus 12, minus 4. 14 minus 8, 6. 7 minus 14, minus 7, right? So this is our first difference data set, right? So if I do first difference of stock price, of Google stock price, I will get something like this. And as you can see, this is clearly well, at least visually, it's stationary. We can run some statistical tests to see something is statistically stationary or not, but that's a topic for the future. But visually, we can say at least the average is constant, right? Compare the average here. So here the average is just increasing. Here the average is constant. So it's more stationary, right? And sometimes we need to do double differencing, right? So maybe if you difference the data once, it's not stationary. You have to do double differencing. What is double differencing? So simply says, we're going to say, we're going to do this process one more time. So minus 4 minus 2, we get minus 6, right? 6 minus minus 4, we get 10, and minus 7 minus 6, we get minus 13, right? So depending on how many times we're going to difference the data, we're going to get either stronger or weaker stationarity, right? Typically, first differencing is enough, but how do we know that it's not enough? We have to run some statistical test and then see if that thing is stationary or not, right? So this is the way to make a non-stationary data set into stationary. One last thing I want to emphasize about differencing is that in general, it helps to stabilize the mean of a time series by removing the changes in the levels. So look at that. This is Google closing price, and as you can see, the means are not stable. However, if I look at the difference data, the mean is a lot more stable. And this is very common in finance literature. So we know that when it comes to stock price predictions in the literature, instead of predicting stock prices, we would be better off to predict stock returns, not prices, right? So, and returns are simply the difference between log values, right? If I say log close price and change the difference, log yt minus log yt minus 1, this is simply the log returns, right? And so don't get confused here. This doesn't mean that if you change prices to returns, you are going to magically get a better model. No, both of them are difficult. The whole point of going from stock prices to returns is that if you're doing long horizon forecasts, the forecasts for your returns are going to be more stable compared to the forecast for the levels. Again, this doesn't mean that because of course you can go back and forth between the two models, right? You can difference, come up with a model, and then undifference, right? So don't think that if you simply go from stock prices to returns, you're going to get a better forecasting models. No, just your forecasts are going to be more stable in the long run. That's it. Okay, this concludes Module 1, Part 1. In this part, we talked about time series basics. Basically, we said in the course, we're going to focus on quantitative time series forecasting task. And we covered some concepts like time series decompositions, diagnostic tools like ACF, PACF plots, and concepts like stationarity. Later on in the modeling section, we're going to rely on these concepts to just basically understand how the modeling works, right? But in order to make sure that you 100% are following what's going on here is that I want to emphasize at its core, the idea is that if we can break down a time series to its components, then maybe we can model each of those components separately. So for example, you can model trend separately, you can model seasonality separately, and you can add those components together, those models in a linear or nonlinear fashion. Then make a forecasting model, right? This is how this field started, right? So basically, this is the you can think of it as a pre-processing part for time series modeling, right? Or feature engineering part. So if this feature engineering, if this time series decomposition, this feature engineering is completely manual, then we get our econometric models. These are the classical time series forecasting models like ETS, ARIMA, the ones that later on we're going to cover in the course. If this feature engineering is completely automated and data-driven, this is basically our deep learning architecture, right? And depending on what machine learning models we're going to use, this feature engineering can be completely manual or automated or something in between, right? All right, so this is, again, as I said, this is what we need for the modeling section of the course. But before doing that, we need to clear some terminologies in terms of forecasting. So we're going to talk about those things in part 2. So until the next one, take care. If you're looking to stay updated with the latest versions of the course's materials, please make sure to follow my GitHub and remember to refresh your repositories periodically. If you find yourself needing a bit more background in econometrics, machine learning, or deep learning, check out my other YouTube videos for additional insights. And for all the latest news and quick updates, don't forget to follow me on Twitter. Thanks for joining me, and let's keep learning together.